This lecture will show you how to configure and program external interrupts, EXTI. External interrupts are generated by peripherals or devices external to the microcontroller, such as push buttons and keypads. There are two approaches to monitoring and responding to external events. One is polling. The other is interrupt. The polling approach is like picking up your phone every few seconds to check whether you are getting a call. The interrupt approach is like waiting for the phone to ring. Apparently, interrupt is more efficient than polling. You are free to do whatever you should do, and pick up the phone only when it rings. Put it simply, an interrupt is essentially a hardware-triggered software action. The interrupt controller temporarily stops the normal flow of program execution, and causes the interrupt service routine to be executed. After the interrupt service routine completes, normal program execution is resumed, at the point where it was last. When there are no interrupt events, the processor runs the normal program, or enters a sleep state to conserve energy. We will use the joystick as an example, to show the basic configuration and programming of external interrupts. Each STM3214 Discovery Kit has a 4-direction joystick. The user may push in one of 4 directions, up, down, left, and right. The user may also press the center of the joystick. Let's quickly review the schematic diagram of STM3214 Discovery Kit. This diagram shows how processors and joysticks pins are connected. GPIO pins PA0, PA1, PA5, PA2, PA3 are connected to the center, left, down, right, and up pin of the joystick, respectively. Each pin is connected to the ground via a capacitor. These capacitors perform hardware debouncing. Here is the internal diagram of the joystick. It has 5 switches. The common terminal is connected to positive 3 volt. When the up of the joystick is pressed, this switch is then closed. As a result, PA2 is then connected to the 3 volt via the common terminal. Pay attention, the joystick center pin is pulled down to ground via a 10 k ohms resistor. Therefore, the default voltage on the center pin is 0. However, the other 4 joystick terminals are not pulled down. If these pins are neither pulled up nor pulled down internally, their voltage is undeterministic. Their default voltage may be high or low, depending on history usage. We can use external interrupts to monitor whether the joystick is pressed or not. Each pin can independently trigger an interrupt request signal. Specifically, software can configure the external interrupt controller, such that PA0 triggers external interrupt 0, PA1 triggers external interrupt 1, PA5 triggers external interrupt 5, PA2 triggers external interrupt 2, and finally, PA3 triggers external interrupt 3. In the next slide, I will show you how to select the source of external interrupts. Both external circuit and the microcontroller can supply a voltage signal on a pin. The external interrupt controller monitors the change of the voltage signal. The rising or falling edge of the voltage signal can make the external interrupt controller generate an interrupt request. The interrupt request will be sent to the NVIC. The external interrupt controller supports 16 external interrupts associated with GPIO pins. These interrupts are named from external interrupt 0 to external interrupt 15. Each of these interrupts is associated with one specific GPIO pin. However, a processor has more than 16 GPIO pins. How does the controller map GPIO pins to external interrupts? STM32 takes a simple approach. Specifically, only pins with the pin number X can be the source of external interrupt X. For example, the source of external interrupt 3 can be PA3, PB3, PC3, PD3, etc. The source selection bits, in the SysCFG external interrupt configuration register, EXTI, specifies which pin will be selected as external interrupt source. Pay attention. No multiple pins from this group can be used as the external interrupt source simultaneously. For example, if the pin PA3 has an external interrupt on it, we cannot use the pins PB3 or PC3 as the source for external interrupt 3. In summary, the controller has one multiplexer for each of these 16 external interrupts. The microcontroller has a total of 16 multiplexers. As shown here, X is from 0 to 15. A multiplexer, also called MUX, is a simple circuit. It selects one of its inputs, and forwards the selected input to the output. The concept of interrupt vector table has been presented in the previous lecture. There are 5 dedicated interrupt handlers for the first 5 external interrupts, including external interrupt 0, external interrupt 1, external interrupt 2, external interrupt 3, and external interrupt 4. For example, pin PA3 can be mapped to external interrupt 3, and its corresponding interrupt handler is EXTI3IRQ handler. External interrupts from number 5 to 9 share the same interrupt handler, EXTI9-5IRQ handler. External interrupts from number 10 to 15 share the same interrupt handler, EXTI15-10IRQ handler. This is the basic diagram of the external interrupt controller. The controller supports 2 types of external interrupts: configurable external interrupts and direct external interrupts. Configurable external interrupts include those associated with GPIO, RTC, comparators, power voltage detector, PVD, and peripheral voltage monitoring, PVM. For these interrupts, the controller has a programmable edge detector, and software can select which active edge generate an interrupt request. An interrupt can be triggered on rising, falling, or both edges. In addition, software can generate an interrupt request by writing one to the Software Interrupt Event Register, SWIER. For direct external interrupts, only rising edge can generate an interrupt request. Direct external interrupts are mostly used for communication peripherals, low-power timer, and LCD. An interrupt can only be generated if the corresponding bit in the interrupt mask register is 1. The interrupt signal can pass this AND gate if and only if the bit from the IMR register is 1. Now, let's work on the software part. If we press the up button of the joystick, software turns on the LED. The up button is connected to GPIO pin PA3, which can generate the external interrupt request 3. Here is the main function. First of all, software must enable the clock of GPIO port A. The constant GPIO AEN is defined in the device header file. This bitwise OR operation sets the least significant bit to 1 in the AHB2ENR register. As a result, the clock signal can pass through this logic AND gate and drive the circuit of port A. Then, software configures the mode of pin PA3 as digital input. This is achieved by clearing 2 bits in the mode register corresponding to pin 3. Specifically, we clear bit 6 and bit 7 in the mode register of GPIO port A. As discussed previously, pin PA3 is neither pulled up nor pulled down externally. It was connected to the ground via a capacitor. If the processor does not pull it down internally, the voltage on pin PA3 is floating. Its voltage can be high or low if the up button is not pressed down. Therefore, the processor has to pull the pin down internally. This is to ensure that the voltage on pin PA3 is low, under the normal state. Here are two lines of C code, which sets PA3 as pull down. Next, we enable external interrupt 3 by calling the function NVIC enable IRQ. Pin 3 in all ports can generate external interrupt 3. These three lines of C code select PA3 as the source of external interrupt 3. When PA3 is selected, the other pins, such as PB3, PC3, PD3, etc., cannot be used to generate external interrupts. Under a normal state, the voltage on pin PA3 is low. When the up button is pressed down, the voltage on PA3 is raised to high. When the up button is released, the voltage on pin PA3 becomes low. This waveform makes two transitions, and has a rising edge and a falling edge. In this example, we select the rising edge as the active edge to trigger external interrupts. Then, software sets the corresponding bit to 1 in the interrupt mask register in order to enable the interrupt request. At the end of the main function, we put a dead loop. After the program performed the initialization of GPIO and external interrupt, the processor will execute this dead loop forever. The next important code is the interrupt handler for external interrupt 3. When the up button is pressed down, the rising edge of the voltage on pin PA3 triggers external interrupt 3. After receiving the interrupt request, the NVIC controller forces the processor to execute the interrupt handler EXTI3 IRQ handler. One of the most common mistakes many people make is that the interrupt handler does not clear the interrupt status or pending flag before it exits. If the interrupt handler does not clear the interrupt pending flag, the interrupt handler will be executed repeatedly by mistake. Please visit the book website for tutorials and project templates.